Okay, this is Mr. G, and I'm very briefly going to talk a little bit about magnets and magnetic fields. So here's a picture of a bar magnet, and bar magnets can influence other magnets and certain types of metals. Magnets exert forces on other magnets. The force can be attraction or repulsion, and magnets also exert forces on certain metals. An attractive force on iron, nickel, and cobalt metals. The way that magnets influence other magnets is via this thing we call a magnetic field. A magnetic field is referred to not as a magnetic field, but a B field. Right? You might think it would be an M field, but no, it's a B field for historic reasons. So the way we picture a magnetic field is similar to the way we did with an electric field. The difference is magnetic field lines always form closed loops. So that field is represented here as coming out of the north pole of this magnet, but then it loops around, and for every magnetic field line coming out of the north pole, it will loop, go back into the south pole, and then guess what? It reconnects inside the magnet. So magnetic field lines always will form closed loops. Okay, and then like electric fields, the density of these magnetic field lines indicates the strength of the magnetic field. And these lines are most dense at these areas where it leaves and goes back in. Those are called the poles. Okay. So this is one way of representing these magnetic field lines. They have a direction and they have a magnitude, so they're vector quantities. And again, they're different from electric fields in that electric fields, those are produced by charges. And so for positive charges, those fields point outward. And for a negative charge, those fields are represented as pointing inward. And the direction of the field represents the direction of the force on a positively charged particle in this electric field. But electric fields here don't necessarily form closed loops. Magnetic fields are always going to form ultimately closed loops, although in some of the situations that we're going to look at in just a second here, we're not going to draw the entire loop. All right. So for example, if you have a bar magnet bent into like a horseshoe shape, then guess what? That's called a horseshoe magnet. And so the magnetic field outside of the magnet here points from north to south. And then you can go up one step further, and let's say this is a really, really big magnet. And so the only parts of the magnet that we can see are going to be the North Pole and the South Pole, okay? The rest of the magnet is too big to fit on the screen. And so now the magnetic field here, this is actually a lot more uniform. And so you really can't even tell that it forms a closed loop. And so this is going to be the way we're going to be talking about magnetic fields in this little brief introduction. All right, so the magnetic fields are going to have a direction and a magnitude, and also B fields are measured in units called Teslas. And so we might write, for example, to be more quantitative, is that, let's say, B is equal to 3 times 10 to the minus 4 Teslas. That is a unit of magnetic field named after Nikola Tesla. Okay. And so we're going to look at how charged particles behave in magnetic fields. All right. So let's draw a little coordinate system here. And this is going to be a 3D coordinate system. So we have X, Y, and yikes, we're going to need a Z direction here, right? So Z, that is pointing out towards you, okay? And so then let's put a magnetic field here. So let's say we have a B field pointing in the plus X direction. And it's a uniform magnetic field. B. Don't worry about the source of this magnetic field. We'll talk about sources of magnetic fields next week. So there's a B field, and let's put a charge right at the origin here. So there's a charged, electrically charged particle, let's say plus Q. And if we let that particle go, if there are no other fields present, just this magnetic field, and we let the charge go, nothing happens to it. It just sits there, okay? Then you might say, well, that's weird, okay? It just sits there. So then you might try moving it, right? If we move the charged particle this way, let's say we give a velocity in the plus X direction. Nothing unusual happens to it, right? We give it a little push. It just keeps on zipping along in the plus X direction according to the law of inertia, right? We stop it and let it go and nothing happens. For that matter, if we take a negatively charged particle and do the same thing to it, nothing happens. And then we could repeat the experiment, but let's move it in this direction, in the minus X direction. And nothing happens noticeable, right? Now, when something does happen is when the charge is moved in a direction that has a component perpendicular to this magnetic field. So, let's do this. Let's take this little charge here, Q, and give it a velocity in the plus Y direction, V, like this. Now, when you do this, something really, really peculiar happens to this guy, right? If you push it upward in the plus Y direction, and there's a magnetic field that is directed in the plus X direction, a magnetic force acts on the particle. And the direction of that force is going to be, to me at least, this seems really super goofy. The direction of the magnetic force on this guy in this situation is away from you. That force is acting in the minus Z direction. And the force is only there while the charge is moving. That's crazy, all right? So yeah, again, a positively charged particle moving in the plus Y direction in a magnetic field directed in the plus X direction gets pushed in the minus Z direction. Okay? You got all that? It could be confusing. There are 3 directions that are required now to understand how charged particles and magnetic fields interact with each other. If you stop pushing the particle up, it stops and just sits there. So there's no magnetic force on a charged particle if it's not moving through the magnetic field, which is really, really curious, okay, if you start to think about this too much, which we'll be doing shortly. So let's look at some other situations here, right? For example, let's do this again. Okay, so X, Y, and Z. I just learned you could draw straight lines with this. I've been using this thing now for, 10 years? And so yeah, you can make a straight line. Boop, just like that. I am so clueless. Anyway, I'm still learning. So now, same magnetic field, all right? That's pointing this way. B. So now, let's take a positively charged particle, plus Q, and let's move it down through this field. Let's give it a velocity in the minus Y direction. So guess what happens now? Yeah, there's going to be a magnetic force on that particle that is directed out of the page. Now that force is directed in the plus z direction, or towards you, all right? But only if the charge is moving. Weird, okay? If the charge moves parallel to the field or anti-parallel to the field, no force. But if it has any component that's perpendicular to the field, there's going to be a force acting on it, okay? And that force will always be perpendicular to the plane containing B and V. Let's just do another couple of examples here, okay? So, for example, consider a oh, not quite perfect. That's okay. X, Y, Z. Let's do a magnetic field pointing up. So here's B, and then here's my charge. So again, move it up, nothing happens. Move it down, nothing happens. But if I move it to the right this time, let's give it a velocity in the plus x direction here. As I've said, there's now going to be a force acting on it. And the direction of that force is perpendicular to the plane containing B and V, which means now the force has got to be either out of the page towards you or into the page away from you. In this case, the direction of the force is going to be out of the page towards you, V. Okay? If the particle, again, if your particle is moved in this situation in the plus x direction in a magnetic field that points up, the force is in the plus z direction. What the heck? How the heck do you even write this as an equation, right? It's one thing to be able to write, okay, if I have an electric charge in a field, the force on that guy is equal to E times Q, right? And the direction of that force, if it's a positive charge, is in the same direction as E. No problem. 2 dimensions. But yeah, we live in at least a 3-dimensional universe. So to deal with magnetic forces for charges in B fields, you need 3 directions. No problem. Enter the cross product, right? So it turns out that the force on a charged particle moving in a magnetic field is equal to Q times V cross, as in big cross, B. Okay, so again, this contraption right here is referred to as a cross product. Okay, it's a way of multiplying vectors. We're familiar with dot products, right? The dot product turns 2 vectors into a scalar, like work is a dot product, all right? But this magnetic force on a charged particle, that's a vector, right? So there's a way of multiplying 2 vectors that gives you a 3rd vector, and that is the cross product, okay? The magnitude, though, here is going to be a little bit easier, and there are some other ways of determining the direction of this cross product, and there's some easy-peasy ways of remembering directions without going into the math details of this. But the math details are actually really, really nice. We'll be getting into more detail about those later. For now, though, let's look at the easy-peasy way of doing this, just using your hand. All right, so this is called the right-hand rule. Imagine your right hand. Okay, so here is, that's my thumb. All right, and then here are my fingers. 1, 2, 3, 4. Check and make sure, right? So, and so this is my palm right here. Okay, so the right hand rule works like this. You're going to let your fingers represent the direction of the magnetic field, B. And then your thumb should be pointing out this way. Your thumb is going to represent the direction of the velocity of the particle. Okay, and finally, your palm gives you the direction of the force on that particle. All right. So all three of these are mutually perpendicular. The magnitude of that force is given by a regular product. It's like I said, it's a way of representing a cross product without using the techniques to get the directions. This gives you the magnitude of force. So that equation for the magnitude of the force is as follows. F is equal to Q, V, B, just regularly multiplying, but times sine theta. So this gives you the force on a charged particle moving through a magnetic field with a velocity v. So again, that's charge measured in coulombs. V is velocity measured in meters per second. And then B is the magnetic field measured in Teslas. And believe it or not, those three come out to give you units of newtons, I promise. All right. Yeah, Tesla is written such that its fundamental dimensions combine with velocity and charge to give you newtons. So nice. Okay. And then the sine theta, that is going to be the angle between these two guys, right? Those are two vectors. They have a direction. And the angle between these two is this theta. So, for example, if this is B and this is V, okay, well, in this case, guess what? Yeah, theta's 90 degrees. And we're going to keep it at 90 degrees for most of the problems that we're doing. And sine of 90 is 1, which means that F, in this case, is just the Q times V times B, okay? And again, in this direction, your fingers are the magnetic field, your thumb is velocity. So yeah, the force on this guy is out this way. All right. And so there are some practice problems I've put up for you to look at. They're not due until for a few days, but if you want to give some of those problems a try, please feel free to do so. And then I think I'm also going to upload a video that you guys could watch if you choose. So there you go. Brief, quick introduction to magnetic fields. It's in your book too, so read about it. And then I'll be back tomorrow to see you guys. All right, so have a good day.